Hello, everyone. Okay, so in this second talk here, what I'd like to do is actually try and help all of you produce animations and pictures, either for class or for research, in a way that makes relatively good quality pictures, but with the least amount of technical training possible. So I've tried to put together a template that will obscure and abstract most of the computational stuff going on and allow you to focus on just the mathematical pieces and know that everything else is taken care of in the background if you so choose. So I really enjoy making animations, but I didn't have any formal training in computer graphics. And so it was kind of intimidating for me to get involved at first with a lot of this software. So I hope this is helpful. Let me show you at first here maybe a couple of animations that I've made recently using the sort of template that I want to help you work with today. So here's an animation from a recent talk about, these are some flat tori from R4 being stereographically projected into R3. And you can draw a couple different ones here. And then if you want to play around with some of my other animations, I've actually used this mostly for teaching this year, since everything's online anyway. It was a good spot to make some teaching tools. So taught calculus, made a Riemann sum grapher. Here's a fun one for doing volumes of revolution, say. Made a little 3D plotter that lets you draw, lets you type in a graph here, top and a bottom curve, revolves it around an axis. We can choose how much of it we want to revolve. We could maybe set the rotation axis to be in different spots. We could move the boundaries, like where we're integrating along, or we could slide the disk and see how the shape of that washer changes. Let's see, a version for cylindrical shells. Maybe if you're teaching parametric equations, here's a grapher where you could type in some parametric equation and it'll draw the curve. Could do the same for surfaces. We'll be working with that today. You could maybe make an analog of that for vector fields. If you're doing vector calc and you need to look at some time varying vector fields, you could make a plotter for that. Here's one for line integrals and so on. So you can play with some of these on my website if you want. This is just to give you a feel for what these look like. And these are all produced using the software ThreeJS, which is a JavaScript library for making 3D graphics. So you can find more information about ThreeJS at their website, threejs.org. They have tons of examples where you can look at the code. If you're familiar with some JavaScript already, you can just download all of their examples and dig in. That's kind of how I started learning. I came with not so much familiarity, so what was really helpful to me was to start out with some sort of an online tutorial. So here's one that I would suggest for people who are interested in digging into this. threejsfundamentals.org was really helpful to me. They give you an introduction to some JavaScript, some very basic coding, and in particular, how to use ThreeJS to set things up. My goal today is not to introduce ThreeJS to you, so I'm going to skip all of the stuff that's covered in this tutorial and give you the lightning fast Cliff Notes version, and then teach you basically how to plug and play with a particular file I've written to hopefully get you producing animations quickly if you would like to. So the Cliff Notes version of what is going on under the hood, the stuff we're not going to talk about, is to set up a program in ThreeJS. There's some basic setup stuff you need to build. You need to build, say, how your computer knows about the camera and how your computer knows the field of view and the size of your screen and how to resize things if you're changing your browser window and so on, all of this sort of stuff. And then your computer also needs inputs from a user. So some of the programs I showed you there at the beginning, you maybe type in a parametric equation. You want it to be a graphing calculator, or you have some sliders. Maybe you want to control how far you numerically integrate something, or you want to control parameters in some sort of a parametric formula or something. Those inputs together produce the scene, which is what the computer has inside, like a three-dimensional scene that you want to draw. And then you also build some sort of a renderer that draws that picture on the screen. And that's the sort of stuff that is done internal to a ThreeJS program. Today, we are just going to focus on that middle step, the scene. The code that I will have you download for those of you who want to participate. Like I was saying, this lecture is really supposed to be more participative, which is kind of weird to do in lecture form, and especially weird to do in virtual lecture form, and especially weird to do in pre-recorded form, I guess. But I will have some code for you to download, and I will encourage you to pause the video and play around and then come to office hours if you want to work on this stuff. So that code you're going to download will have all of the gray stuff here worked out where you won't have to touch any of it. And so what we're going to focus on is how do you build the three-dimensional scene that you want to draw? How do you tell the computer to draw the mathematical objects you're interested in? And so the structure of a scene in ThreeJS, the way that we're going to describe objects to the computer, is ThreeJS thinks of three-dimensional objects that you want to draw as meshes. So if you had two different objects, you want to maybe draw a cube and a sphere, you would say there's two meshes in your scene. There's a mesh for a cube and a mesh for a sphere. And each mesh in your scene, each object, is built out of two types of things. It has a geometry and then a material attached to it. The geometry you can think of as controlling the shape of the object, and the material controls like the color of the object. And so to look at an example of that in code, here's an actual example cut and paste from a program I had. This just draws a sphere. So we tell the computer here the geometry. ThreeJS has a bunch of built-in shapes. So it has a built-in geometry for a sphere. We're telling it to draw a sphere. And then we're telling it a certain material to use. Here I'm telling it to color it using the normal vector on the sphere. And once you've determined the shape and the color, you build a mesh using that shape and using that color, and you add it to a scene. This is the part of the program that we are interested in. Changing out the geometry and changing out the material changes what you see. And if you want to play around with this without worrying about any of the overhead, here is a web address you can copy or type into your browser. I will pull it up here. Okay, so here I've pulled up the little sandbox for playing around with this program. In the window here is this entire JavaScript program for running this ThreeJS piece. We don't need to worry about all of this. What we're going to focus on is the part we saw on the last slide, namely how to define an object. We need to define a geometry and then a material, and then we need to add it to our scene as a mesh. So here you can see the geometry, the shape I've defined is sphere geometry. It's one of the built-in geometries in ThreeJS. And so it's drawing a sphere over here. And I'm coloring it by the normal vector, just like in the code I showed you. Now, if I change that out and I replace that, say, with a cube geometry, and now I run this, it draws a cube. And if I change that out again, there's tons of built-in geometries in ThreeJS. A particularly fun one is the torus knot geometry. It'll draw torus knots for you. So here's what happens when I switch out that geometry. And you could switch out the material as well. I'm not going to focus on that here. There's lots of choices for material, and you could read about this if you wanted to on the ThreeJS website. But okay, so that is the basics of how geometries and materials combine to build an object in ThreeJS. Those objects we saw are pretty basic looking. And that was, at least for me, one of the barriers on getting into animation is you are trying to learn how to code this stuff, and your pictures in the end don't end up looking very good. So what I'd like to do is try and jump in to digging into some code that I wrote that hopefully lets you produce nice looking images without having to worry about those details. So here's some examples that I made with it. And here is what I mean by I want us to be able to focus on the math. So I've put together something that lets us draw parametric curves and parametric surfaces, where your input to the program is really just writing a function like this. There's a function in the code that's going to be called parametric surface point, and it takes in two parameters, u and v, which are parameters on the surface. And then it also optionally takes in a parameter named time that would let you animate. And what you need to do is just specify how x, y, and z depend on u and v. So in this example here, my parametric surface point function here is just drawing the graph of the function x times y. It's setting x equal to u, y equal to v, and then z equal to their product. So this is just the graph's f of xy equals xy. But this is what it would look like in code. So to get playing around with this, the first thing you need is an editor. So if you're already in this kind of stuff and you have a favorite editor, great, you can use that. You might need to run a local web server to work on some of this stuff. So, but if you have a web, if you have an editor you like, just set up a local web server through your terminal or something, navigate over to your folder, you're good to go. If you don't have one, and this is your first time working with something like this, I would recommend checking out this one called WebStorm because it takes care of that for you. And so I'll use that in our example so you can see. Let me pull this up here. Great. So yeah, if you wanted to, if you are just completely starting out, you've never worked with this stuff before, and you want to download this, go find WebStorm's website. The nice thing is if you go over to buy and to individual use, it's actually free for academics. Oh, special offers, sorry, not individual use. It's free for people here with an edu email. So you can download it, you can register with your email or however, and get a copy. So great, let's say you have a code editor that you like and that you want to use. The next thing to do is to download this set of code from my GitHub. This is what we will be practicing with together. So go to github.com/me. I have that pulled up here as well. I'll show you, and we're going to download the project called ThreeJS parametric template. That's the template I wrote for this talk. So let's go to my GitHub. Here we go. This is what you'll see. Go over, click on repositories here if you want to find them. And this one here, ThreeJS parametric template. If you click on that, you'll see there's a folder with some code here. You can actually just download all the code. So like download it maybe as a zip folder or something, unzip it, put it where you want on your computer. And then we're going to open that in our code editor. So now that I have that downloaded, I will open it in WebStorm here. So this is what it would look like. Actually, maybe I'll go back to the slides here for just a second. Great. Oh yeah, I took screenshots of this. So here is the contents of what you just downloaded. You can see there's a bunch of files in here. These are the files that are taking care of all the background stuff. For our purposes today, I've tried to put everything that you need to edit into a single file. So if you are just starting out, you can ignore everything in here except the file called calculations.js. That's where the math is being injected into the program. And then if you want to learn more ThreeJS in the future, you can take a look at these other files in the context of other ThreeJS examples or some of those tutorials I was recommending. But for now, we're just going to dig into that one file. And so what that file is going to do is let us specify a parametric surface and a parametric curve by implementing two functions that just tell us how to get the points, like you saw on that f of xy equals xy example. Now, the default example that loads when you download my code, it could have been the graph of xy, but I figured it'd be more fun to draw something cooler. So I actually just Googled fun parametric surfaces, came across this Wikipedia page with a surface people call the seashell surface because it looks like this. It's a cylindrical tube that has been rescaled exponentially. And here's the parametric equation for that. So taking that equation and translating that into code gives us this. And we will look at this in the actual code in just a second. I will show you exactly where this is copied and pasted from. So the point is that our goal is going to be to write a function like this, parametric surface point U and V that it takes in are always going to be numbers between 0 and 1. That's just to make something nice and uniform that's everywhere. And so if you have different parameters you want, you're going to have to rescale them. So that's what I've done here. I set U min to 0, U max to 2 pi. So U goes between 0 and 2 pi now. And V goes between negative 2 pi and 2 pi. And then I just typed in the parametric equation in JavaScript from that Wikipedia entry. So these 3 lines here, X, Y, and Z, are just verbatim these 3 lines. And when we run that, we will see the seashell surface. So let's go run that right now. I'm going to move over to the code editor so we can run this live. Okay, here we are in WebStorm. So actually, I got to shrink this. I'm worried that my video, however Zoom captures it, might be covering this. So let me move it down so I'm not in the way. Okay, so to run the program, if you open the file index.html, that's like the main file where things will run from. We don't need to edit any code in here. Remember, we only need to edit this file called calculations. But if you want to run the program from WebStorm, if you open that, you'll see browsers that you have installed on your computer show up as icons here. And you can click one of them and it'll run the program in that browser for you. So I just clicked Chrome. So now it's running live in Chrome. You can see the surface being drawn. So great. It looks just like it's supposed to. Everything's working good. So now let's go look at the code. Let's look at how to do that. So if you look over at the sidebar, we can dig into this code, go in. Remember, we can ignore everything that we want to, except this file called calculations, which I have open here. It's a little bigger. Dig down, and there are 2 functions in here. There's a function called parametric surface point and a function called parametric curve point. For the moment, we're just going to look at the parametric surface. So this is exactly what I showed you on the previous slide. Let me maybe pull the image back up again. There we go. Great. So that is what's running live right now. It's just that function. Parametric surface point is what's running right here. Parametric curve is actually drawing the little end of the shell here, but we'll worry about that in a second. What I want to show you is once you put that in, the rest of the program in the background will help you out in the sense that I've put in some stuff that will let you change the opacity of the surface. So you can draw a clear surface, you can draw a completely opaque surface in between. You can change how reflective the surface is. You can make it really shiny and make it not really shiny. You can change the color here with a little drop down thing, so you don't have to worry about doing that in code. And when we deal with the parametric curve in a second, you'll see there's the same sort of controls here. You can change the color of that parametric curve. We could change the resolutions as well. This is just like, or the thickness here. This one's an important one. You could change how thick the tube that you're drawing is. And lastly, I have built in some sliders here. You can use the letters A, B, and C in your parametric equations as parameters. So here I put them in the formula so I can stretch my seashell. You can stretch them using these little sliders. Okay, so let's go back to the code. So you can see those A, B, and C that I use as affine stretches. I just multiplied X by A, Y by B, and Z by C. I have this set up in here, taken care of for you, so you can just use the letters A, B, and C. And the computer knows that they're hooked up to those sliders already. Okay, so that is the default example. I'm going to comment that out. And we're going to look below here. I have a second example that is less fun, but maybe easier to get started with. So I will uncomment this so we can play around with this and you can see how we get a new surface. Let's take a look. There's a function here, parametric surface point. I've told you that U ranges from -3 to 3, V ranges from -3 to 3. And then I have the 3 parameters A, B, and C, just like I had above. And now here's the part that you would change if you want to draw a new surface. You just have to set what X, Y, and Z are in terms of U and V and A, B, and C. And if you want the parameter time. Here, I've set it to be the graph of sine of AX times sine of BY. So this will draw that graph. And then I have a second function here, parametric curve point. Instead of taking in UV like a surface, a curve would just take in one parameter, which I've labeled S. S is again between 0 and 1. First thing I do is rescale it between 0 and 2 pi. And then get the letters A, B, and C from those sliders. And then the only part that you would need to change if you want to make your own function are what is the parametric curve? What are X, Y, and Z in terms of S and ABC and time? So here it is cosine AS, sine BS, and cosine CS. Oh, yeah, okay. That's the wrong one. I need this one. Let me run this. So I didn't worry about separating them, so they're just being overlapped right now. But all I want to show you is what happens when we change the parameters. So this is our surface, sine of AX times sine of BY, and then our curve. And as I change the A parameter, it would change your surface, same with the B parameter. And the C parameter was involved in the curve, but not the surface. So it'll change that. And then, of course, we could change any of these we want to. We could switch the resolutions. We could make it really shiny and red, say. So these two slides, this is really the summary of the two functions that you would need to implement if you want to use this code to make images for yourself. Here's the inputs. U and V in 0, 1, the parameters in 0, 1, and time in R, and the output, you need to give me X, Y, and Z. And same for the parametric curve. So in closing, maybe I'll just change one of these formulas. Let me change the surface. Let's see what happens if I make this not just sine of AX times sine of BY, but sine of AX times sine of BY times sine of X times Y times time. Just get time in there and see what happens. I'll save that and we'll run it. So now you can see the surface is animating, it's changing in time. I'm going to run out of resolution here pretty quick. I probably should have picked a better surface equation, but there we go. The point is that you can use the word time as it's a real valued variable that's just monotonically increasing. Like it's measured in seconds on your computer. So you can you can use ABC, but you can also use time in any of the formulas you want. You can type any parametric equation in here without changing any of the rest of the code. Same for here. You can type any parametric equation in here without changing the rest of the code. So yeah, I hope this is helpful to some of you. With a little bit of practice, it should allow you to produce nice looking animations for any virtual talks you give or for classes where you just need parametric functions and curves. I guess I will close by saying if you don't want the parametric curve and surface overlapping like they were there, if you want one or the other, you can disable them by going over to the file called mesh. Remember, mesh is where the meshes are the objects that we're putting in the scene. And in mesh, I have labeled here a spot that makes a surface and a spot that makes a curve. And then later we update when we're animating the surface and the curve. And so if you wanted to get rid of the curve, we will just comment everything that says curve. So down here, that all says surface, this says curve, this says curve. Get rid of all that. Now there's only surfaces. And so it only draws the surface. And same thing, if I commented out everything that said surface and left the curve, then I would get only the curve. So that's really all you would need to edit. You can make your two parametric functions and you can turn them on and off in the meshes folder, or in the meshes file. Well, great. Well, yes, feel free to come ask me questions, or if you want to try and build something together in office hours, let me know. And have a great day.